last lecture, we had discussed the two particle problem in which there were two masses m1 and m2, and the potential energy describing their interaction depended only on the distance between the two particles. So, we considered two particles m1 and m2, and the coordinates of this point are x1, y1, z1, and the coordinates of this point of this mass is x2, y2 and z2. So, this is vectorially represented by r1 vector and this is by r2 vector, and the potential energy describing the interaction between the two particles depends only on the magnitude of the distance, between the two particles. So, that is a central force potential, that is known as a central potential V of r. So, we wrote down the Hamiltonian for the two particles and we said this is P1 square by 2 m1. So, which is h cross square by 2 m1 delta 2 by delta x1 square plus delta 2 by delta y1 square plus delta 2 by delta z1 square minus h cross square by 2 m2, and the coordinates of the second particle delta 2 by delta x2 square plus delta 2 by delta y2 square plus delta 2 by delta z2 square plus the potential energy which depends only on the magnitude of r1 minus r2, and this is represented by small r. So, if you want to solve this equation h psi r1 r2, this is a function therefore of 6 variables, this is equal to E psi of r1 r2. Then if we assume a separation of variables in which psi of r1 r2 is a function of r1 multiplied by another function of r2, then the method of separation of variables will not work. Indeed, we introduced two coordinates. One is the center of mass coordinates m1 r1 plus m2 r2 divided by m1 plus m2, and then the relative coordinate r is equal to r1 minus r2. In terms of these coordinates, we found that the Hamiltonian operator becomes h cross square by 2 m, where m is equal to m1 plus m2 delta 2 by delta capital X square plus delta 2 by delta capital Y square plus delta 2 by delta z square. These are the x, y, z coordinates of the center of mass, and m is the total mass, the mass of the center of mass, minus h cross square by 2 mu, and the in terms of the relative coordinates. So, we will just write del square, where del square is equal to, defined to be equal to delta 2 by delta x square plus delta 2 by delta y square plus delta 2 by delta z square in terms of the relative coordinates, and plus the potential energy function which depends only on the magnitude of r. So, if we now try to solve the Schrodinger equation, which is now psi which depends on r and small r, then we found that the method of separation of variables would work. So, if I assume a solution like this, psi of r comma r is equal to phi of r and psi of r, then the method of separation of variable will work. Here, as I had mentioned in my last lecture, mu is the reduced mass of the two particles, which is given by m1 plus m2. Actually, the definition of the reduced mass is 1 over mu is equal to 1 over m1 plus m1 over m2. So, we can simplify it and obtain this. So, this function phi of r we discussed, this is the translational motion of the center of mass, free translational motion of the center of mass. So, we solved the equation and we found that capital phi of r was e to the power of I p dot r by h cross. So, where p square by 2 capital M represents the center of mass energy, represents the energy of the center of mass. And then the wave function psi of r satisfies the following equations: del square of psi plus 2 mu by h cross square E minus V of r psi, which is now a function of r theta phi, where small r, small theta, small phi are the coordinates corresponding to the to this vector r is equal to r1 minus r2. This is equal to 0. So, therefore, we found that a two particle problem can be reduced to two parts. One describes the free translational motion of the center of mass, and the other which describes the internal motion of the two particles, relative motion of the two particles, which satisfies the three-dimensional Schrodinger equation with the potential, with a spherically symmetric potential energy function. Here we have to replace the mass is the reduced mass of the two particles, that is m1 m2 by m1 plus m2. This is a rigorously correct solution for any two particle problem, and we will apply this to the hydrogen atom, which consists of a proton and the electron. We will also consider the solution corresponding to the deuteron problem, which is the fundamental problem in nuclear physics, describing neutron and the proton. And we will also discuss the fundamental problem in molecular spectra, namely a molecule consists of two atoms. There also one gets an equation similar to this, and we will solve that. So, the solution of this equation is of extreme importance in atomic physics, in nuclear physics, and in molecular spectroscopy. So, we have to carefully understand the solution of this equation. So, we will use the spherical polar coordinate system, and in which the wave function, the del square operator, del square operator is given by 1 by r square. This we must remember, r square del psi by del r plus 1 over r square within brackets 1 over sine theta delta by delta theta sine theta delta psi by delta theta plus 1 over sine square theta delta 2 psi by delta phi square. So, this is the del square operator, and as you may recall that the angular momentum operator, the square of the angular momentum operator operating on any wave function psi. So, this was, as you may recall, this is Lx square plus Ly square plus Lz square, and we had obtained expressions for Lz and similarly for Lx and Ly. and if I square and add them, so this becomes minus h cross square 1 over sin theta delta theta delta by delta theta sin theta delta psi by delta theta plus 1 over sin square theta delta 2 psi by delta phi square. So, we see that the quantity inside the brackets, square brackets, are the same. So, therefore, this quantity is equal to minus L square psi by h cross square. So, therefore, del square of psi is equal to 1 over r square delta by delta r square delta psi by delta r minus L square psi by r square h cross square, and if I substitute this expression here, so del square psi, so this equation becomes plus 2 mu by h cross square E minus V of r psi of r theta phi is equal to 0. So, the potential energy function does not depend on theta and phi, it only depends on the magnitude of the distance between the two particles. Such a potential is known as a spherically symmetric potential. Spherically symmetric potential. Now, the solution of this equation is fairly straightforward. So, what we do is that we use the method of separation of variables and we write this as psi of r theta phi is equal to a function of r times a function of theta phi. So, if I substitute this in this equation, then y I can take outside. So, I get y theta phi, please see this, divided by r square, and since this is a function of r only, so this becomes a total differential d by dr r square dr by dr. What I will do is take this to the other side of the equation. So, you will get plus 2 mu by h cross square E minus V of r of r y theta phi is equal to L square, which depends only on theta and phi. L square depends only on theta and phi. So, I can take the r of r outside, L square y divided by r square h cross square. Now, the variables have still not separated out. This has r theta and phi, this has r theta and phi, this also has. However, if I multiply the whole equation by r square divided by r of r and y theta of I, then the first term will become the y will cancel out. So, we will, and r square will also cancel out. So, it will be 1 over r ddr multiplied by r square dr by dr and then plus 2 mu r square by h cross square, because I have multiplied by r square and I have divided by r times y. So, this two terms cancel out. So, I will have E minus V of r. This will be equal to, the r square will cancel out, r y will cancel out, L square y by h cross square. So, L square involves only theta and phi, y involves only theta and phi, and r involves, r is a function of r only. So, the variables have indeed separated out. This is a function of r only and this is a function of theta only. So, a function of r cannot be equal to a function of theta unless both of them, oh, this has to be divided by y, this has to be divided by y. So, this is y. So, divided by y theta phi. So, this must be equal to a constant. So, the left hand side is a function of r, the right hand side is a function of theta and phi, and we say that the method of separation of variables has worked, and a function of r can be equal to a function of theta and phi only if both of them are equal to a constant. So, therefore, if I write this, I will get L square y of theta phi is equal to lambda h cross square y theta phi. Now, this is the equation determining the eigenvalues and eigenfunctions of the operator L square, and we had found that the values of lambda, the eigenvalues of the operator L square is equal to L into L plus 1, where L would be 0, 1, 2, 3, etc. Only then, only for these values of L, this equation will have a well behaved solution, and y theta phi are spherical harmonics, y L m theta phi, and for each value of m, for each value of L, m will go from minus L to plus L, including 0. So, these, as we had discussed in our last lecture, these are the spherical harmonics, and we had shown that for example, y L m theta phi, this is a function of theta times the phi dependence was of the form of root 2 pi e to the power of I m phi. So, therefore, y L m theta phi are simultaneous eigenfunctions of L square as well as of L z. So, L z y L m theta phi, L z, if you may recall, has the operator which we had derived from first principles, minus I h cross delta by delta phi. So, this is equal to m h cross y L m theta phi, because the phi dependence is of the order of the form of e to the power of I m phi, and if I differentiate with respect to phi, I will get I m, and if I multiply by minus I h cross as it is here, so then you will get m h cross. These are the eigenvalues of. So, y L m theta phi are simultaneous eigenfunctions. This we all must remember, of the operators L square and L z. And as we had discussed, we had also shown that y L for m equal to 0. So, this is under root of 2 pi, and these are proportional to P L of cos theta. So, the normalization constant was 2 L plus 1 divided by 2. So, this is for m equal to 0, for m equal to 0. For arbitrary value of L and m, the spherical harmonics are little complicated, and we will discuss this little later, maybe about 6-7 lectures later. So, y theta phi, so this term gives me an eigenvalue equation, and we have shown that lambda must be equal to L into L plus 1. And so, therefore, let me write down the, so lambda is equal to L into L plus 1. So, let me write the radial part of the equation. So, this is 1 over r d dr into r square dr by dr plus 2 mu r square by h cross square E minus V of r, and I take L into L plus 1 on the left hand side. So, you will be minus L into L plus 1, and since I have taken inside the brackets, so I must multiply by h cross square divide by 2 mu r square, r of r, sorry, this is equal to 0. The next step is I multiply by r of r divided by r square of r. So, this becomes 1 over r square d dr r square dr by dr plus 2 mu by h cross square E minus V of r minus L into L plus 1 h cross square by 2 mu r square, r of r equal to 0. So, this equation is known as the radial part of the Schrodinger equation. This is an extremely important equation, and we should all remember this. This is known as the radial part of the Schrodinger equation. So, if we solve this equation, we will obtain the eigenvalues of the problem. Please notice that we still have not specified V of r. So, we have carried out an important simplification for any central force potential. That is, if we consider two particles, and if the potential energy describing the interaction between the two particles depends only on the distance, then the three-dimensional Schrodinger equation can always be simplified in terms of only one variable. So, we do not have to solve in each case the three-dimensional Schrodinger equation. We just have to solve one equation involving the radial coordinate r. So, this is a major simplification which is possible only when the potential is spherically symmetric, that is, V depends only on r. There is another simplification possible if I define a new variable which is u of r by r, that is, u of r is defined as r times r of r. So, this is the definition, this equation represents the definition of u of r. Then a simplification occurs because dr by dr, if I differentiate this, this becomes minus 1 over r square u of r plus 1 over r du by dr. In this, there is an r square term here. So, if I multiply this by r square, dr by dr, please leave some space here. So, if I multiply by r square, it becomes minus u of r plus r times du by dr. Then I must differentiate this with respect to r. So, I differentiate this. So, I differentiate this with respect to r. So, this will become minus du by dr plus du by dr, because the differential coefficient of r with respect to r is unity, plus r d2u by dr square. And you can see this term cancels out with this term. So, if I divide by r square, so we get r square. So, divide by r square. So, we will get 1 over r d2u by dr square. So, this term becomes 1 over r d2u by dr square. And here this term will become u of r by r. So, the r cancels out and we finally obtain, I hope you understand. So, let me do this once again. So, you have 1 over r d2u by dr square. So, you write down 1 over r d2u by dr square plus 2 mu by h cross square E minus V minus L into L plus 1 H cross square by 2 mu r square. This is the term due to the L square operator or the orbital angular momentum multiplied by r of r. R of r is u of r divided by r. So, this is what I tried to say, this r and this r cancel out and we get a very simplified equation that d2u by dr square plus 2 mu by h cross square E minus V of r minus L into L plus 1 h cross square by 2 mu r square multiplied by u of r is equal to 0. This is also known as the radial part of the Schrodinger equation, and this you must remember this by, and L is equal to 0, 1, 2, 3, etc. We will solve this equation for the hydrogen atom problem, actually for hydrogen like atom. So, that for helium plus atom, for the deuterium atom problem, for the lithium doubly ionized which consists of 1 electron. So, essentially for all 1 electron atom problem. And we will also solve for the deuteron problem, that is 2 particles like neutron and proton, and we will also solve the same equation for a diatomic molecule like hydrogen chloride diatomic molecule, and we will get what are known as the rotational and vibrational spectra of the diatomic molecules. So, let me first consider the simplest of the atoms, namely the hydrogen atom. As we all know, hydrogen atom consists of an electron and a proton. The proton is about 1836 times heavier than the electron. So, the reduced mass of the hydrogen atom will be MEmP divided by Me plus Mp. So, you have here, I have written down in any book, including in our book, we have given the accurate values of the rest mass of the electron, which is 9.109387 into 10 to the power of minus 31 kg. Sorry, this is for the deuteron. Sorry. So, this is for the proton. The rest mass of the proton is 1.6726231. So, the rest mass corresponding to the hydrogen atom is MEmP divided by Me plus Mp is 9.1045 into 10 to the power of minus 31 kilograms. If we solve the, if we consider the deuterium atom, so this is the rest mass of the deuteron, which consists of a neutron and a proton, is so much. So, you have the deuterium atom, which consists of a proton and a neutron and a single electron. This is the nucleus. This is the nucleus. So, the analysis of the deuterium atom is the same as that of the hydrogen atom, except now the rest mass of the deuteron, the nucleus, is now slightly more. So, we will first consider the hydrogen atom problem, in which the hydrogen atom consists of, as I mentioned, the electron and the proton, and whose reduced mass is given by 9.1045 into 10 to the power of minus 31 kg. And the potential energy describing this interaction is given by, in the CGS system of units, we will use the CGS system of units. This is given by the V of r is equal to minus E square by r in the CGS system. In the MKS system of units, it will be minus Q square by 4 pi epsilon naught r, where Q is the charge of the electron measured in coulombs, and epsilon 0 is the dielectric permittivity of free space. So, as we all know that epsilon 0 is equal to 8.854 into 10 to the power of minus 12 MKS units. So, just for the sake of convenience, we will use the CGS system of units. However, if there is a dimensionless constant, which is known as the fine structure constant alpha, which is given by E square by h cross c. This value is approximately equal to 1 over 37. So, if I replace E square by alpha h cross c, then that formula is valid both in the MKS system of units as well as in the CGS system of units. So, if I write V of r as equal to minus alpha h cross c by r, then this formula is valid both in the MKS system of units as well as in the CGS system of units. Okay. So, let me write down the we can use this formula or this formula, it does not matter. So, our objective is to solve this equation. Our objective is to solve this radial part of the Schrodinger equation with V of r given by minus E square by r. Or actually, if we consider an atom whose nucleus has a charge Ze, then it will be minus Ze square by r. So, we will assume that let us suppose the nucleus has a charge Ze. So, the potential energy will be given by minus Ze square by r. So, we will have d2u by dr square plus 2 mu by h cross square. We will solve for the bound states for which E is negative, and when you have proton and electron, the total energy of the hydrogen atom is negative. So, those are the bound states of the problem. So, the energy E will be negative. So, E minus V of r. So, this will be plus Z E square by r minus L into L plus 1 H cross square by 2 mu r square. U of r is equal to 0. Now, let me write it in terms of a dimensionless unit, so that it looks a little simpler. So, we define a coordinate rho which is equal to gamma r. We still do not know what is the value of gamma, and we will choose gamma appropriately. So, we will have du, just as we did in our harmonic oscillator problem, du by dr is equal to du by d rho into d rho by dr. So, that is gamma. If I differentiate this again, so you will have d2u by dr square is equal to gamma square d2u by du square. So, I substitute it here and then divide the whole expression by gamma square. So, you get, please see this, I substitute for d2u by dr square here and write gamma square d2u by dr. So, you write d2u by d rho square plus, if I take 2 mu by h cross square outside, 2 mu e by h cross square gamma square plus 2 mu z e square by h cross square. Please see this, r is rho by gamma, and then I have divided by gamma square. So, this will be gamma square in the denominator. So, 1 gamma will cancel out. So, this will be gamma times 1 by rho. And you please see this 2 mu by h cross square will cancel out. So, this will be L into L plus 1, and I have divided by gamma square. So, this will be gamma square r square. So, this will be rho square. I still have not chosen the value of gamma. Just as we did in our harmonic oscillator problem, we choose gamma such that, E is negative. So, this quantity is minus 1 by 4. So, 2 mu by h cross square gamma square is equal to minus 1 by 4. So, therefore, this implies that gamma square is equal to minus 8 mu e by h cross square. This is the definition of gamma. I am assuming E to be negative, bound state problems. E is less than 0, which corresponds to the bound state problem. So, I choose gamma square is equal to minus 8 mu e by h cross. So, that here this factor I will replace by minus 1 by 4. I write this, I define this as lambda, and this quantity is rho square, gamma square r square is rho square. So, that this equation simplifies to the following. So, the above equation becomes d2u by d rho square plus minus 1 by 4 plus lambda by rho minus L into L plus 1 by rho square. U of rho is equal to 0, where gamma square is so much, and also we have lambda is defined to be equal to 2 mu z e square by h cross square gamma. Gamma is this. We will calculate this explicitly little later. So, this is the radial part of the Schrodinger equation, to which it is simplified for the hydrogen like atom problem, in which the potential energy function, the charge of the nucleus is Z e, and therefore, the potential energy function is r. R is the distance between the nucleus, which is assumed to be a point, and the electron. Now, I want to solve this equation, and in such equation, as we had done for the harmonic oscillator problem, we look for solutions both for rho tending to 0 and rho tending to infinity. Now, let us take the simple case. So, as rho tends to infinity, this term and this term becomes negligible. So, I can neglect this. So, d2u by d rho square minus 1 by 4 u of rho is equal to 0. So, the solution is u of rho becomes e to the power of either plus half rho or minus half rho. We will choose the minus sign, because plus half rho will blow up at infinity. Then as rho tends to 0, this term is very important, because this goes to infinity faster than this is a constant, this is faster. So, as rho tends to infinity, sorry, this is d2u by d rho square. So, the radial part of the Schrodinger equation becomes, if we neglect the other two terms, is equal to L into L plus 1 by rho square. Now, the solution which is well behaved at rho equal to 0, as you can see, is rho to the power of L plus 1, because if I substitute this, if I differentiate this twice, if I differentiate it once, I will get L plus 1 rho to the power of L, and if I differentiate it again, I get L into L plus 1 rho to the power of L minus 2. So, my left hand side becomes L into L plus 1 rho to the power of L minus 2, and the right hand side becomes L into L plus 1. This is rho to the power of L plus, sorry, this is L minus 1, I am sorry. So, rho to the power of L plus 1 minus 2. So, this will be rho to the power of L minus. So, this is the solution to which it tends to as rho tends to 0. So, these two limiting forms suggest that we try out a solution like this. U of rho is equal to rho to the power of L plus 1 e to the power of minus rho by 2 into y of rho, or I write this down as g of rho times y of rho, where g of rho is identically equal to rho to the power of L plus 1 minus e to the power of minus rho by 2. I hope this is clear. Now, if I differentiate it once, so you will get u prime will be g y prime plus y g prime If I differentiate this again, you will get g y double prime plus y prime g prime from here 2 g prime y prime plus g double prime y. So, therefore, we will have that u of rho, if it is g of rho y of rho, then u double prime of rho, if I differentiate this equation twice, so it will be g of rho y double prime of rho plus 2 g prime y prime plus g double prime y of rho, where g of rho is equal to rho to the power of L plus 1 e to the power of minus rho by 2. Let me differentiate this. So, g prime of rho, because I need g prime and g double prime. So, g prime of rho is equal to L plus 1 multiplied by rho to the power of L into e to the power of minus L rho by 2, which I will take outside. And if I differentiate this, so this will become minus rho to the power of L plus 1 divided by 2, a half sign, because so multiplied by e to the power of minus rho by 2. So, if I rho to the power of L plus 1, if I take outside, so you get L plus 1 divided by rho minus half rho to the power of L plus 1 multiplied by this. So, that is g of rho. So, g double prime of rho, if I differentiate this again, the differential coefficient of this term will be minus L plus 1 by rho square multiplied by g of rho plus L plus 1 by rho minus half times g prime of rho. But g prime of rho is this times g of rho. So, this will be square of g of rho. I hope this is clear. So, as I have differentiated this once, so first I differentiate this term. So, this will be minus 1 over rho square, and then I differentiate this g prime of rho. So, this will be g prime of rho is L plus 1 by rho minus half into g of rho. So, this becomes square. So, this becomes, please see this. So, this is L plus 1 whole square, L plus 1 whole square by rho square minus L plus 1 divided by rho square, and the square of this is, or if I multiply the square of this, so this will be 2 L plus 1 by rho and then plus 1 by 4 g of rho. So, if you take L plus 1 whole square out bracket, so L plus 1 minus 1, so that is L. So, this becomes L into L plus 1 by rho square minus L plus 1 by rho plus 1 by 4 g of rho. Now, I have the expression for g prime of rho, I have the expression for g double prime of rho. So, therefore, u double prime, this is a little laborious algebra, but fairly straightforward, that you will have u double prime will be equal to, as we had said, that g y double prime plus 2 g prime y prime plus G double prime y. So this will be, first of all, the first term will be G y double prime plus 2 G prime. G prime will be 2 L plus 1 by rho minus half times G into y prime, and plus G double prime, plus G double prime is equal to L into L plus 1 by rho square minus L plus 1 by rho plus 1 by 4 into G of rho times y. This is u double prime, and if I recollect, my radial part of the Schrodinger equation had these three terms, d2u by d rho square plus within brackets minus 1 by 4 plus lambda by rho minus lambda in L into L plus 1 by rho square. So, I put it here. So, my radial part of the Schrodinger equation becomes plus within brackets minus 1 by 4 plus lambda by rho minus L into L plus 1 by rho square times u. U is G times y. So, the G cancels out everywhere, and if you carefully see, this minus 1 by 4 cancels out with this minus 1 by 4. These are rigorously correct solutions. This term cancels out with this term. So, if I multiply by, so the G's also cancel out, G cancels out from here, 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 here. So, we will have, if I multiply this by rho, so then I get rho d2y by d rho square plus, if I take 2 inside, 2L plus 2, 2L plus 2 minus rho, because I have multiplied by rho, dy by d rho plus, I have here, I have multiplied by rho. So, this rho cancels out, lambda minus L minus 1, y of rho is equal to 0. Now, this is the equation. If you recall that this is very similar to the confluent hypergeometric equation that we had written down earlier. Before we finish this class, I would like to mention that we had obtained asymptotic forms for u of rho, for rho tending to infinity as e to the power of minus half rho, for rho tending to 0 as rho to the power of L plus 1. So, these two helped us to write the solution in this form, but this is a rigorously correct solution, rigorously correct solution. There is no approximation here. So, y of rho is defined by this equation, and y of rho now satisfies this particular equation. So, if I am able to solve this equation, then I would have obtained a rigorously correct solution of the Schrodinger equation, of the radial part of the Schrodinger equation for the hydrogen atom problem or for the hydrogen like atom problem. So, these are all rigorously correct solutions. I want to emphasize that. Thank you.